G'day champions. So back in December we had a quick look at this Strauss Polka, Australian made amp, and now I'm gonna get stuck into it. First we're gonna give it a clean, check all the components for drift, and just see if we can find any bad connections, that kind of thing. Then we'll give it some reduced voltage and just check that all the voltages are present where they should be, and then we might start doing things that we know we're going to do, like replace that cap when the last tech's only replaced 1 out of 2. There's only that's the only filtering in the amp. They're dual section caps, by the way. And then any other electrolytics, we've got a couple down there in the bias supply, and we've got some, oh sorry, over there in the bias supply we've got some bypass caps in there. We'll change out. We'll just give the thing a clean and see where it's at. So I want to fire it up with minimal labour first, just to confirm that like the transformers are okay and that there's no major showstoppers, and then we'll give it some signal after that and just see if there's any creases left to iron out. So I've checked all these components for drift and they're all pretty good actually, all within tolerance. So we'll just give this board a clean. As you can see, she's quite dusty. But to get to the preamp board, because that's housed down in this little section of the chassis here, you can see the pots there. They actually, the shaft passes through the circuit board, and then that passes through the front panel to the knobs at the front. So to get that out, that is mechanically fixed by the pots. I need to remove the knobs and the nuts, and then these jacks over here, and take the whole lot out down through the bottom where there's more slack on the cables. While I've got it out, I might stick a grommet on that hole down there, because that's cable direct to the sharp metal edge. That's not great. And we'll check for drift on these components and replace the bypass cap. I think there's only one by the looks of it, and just inspect the thing for any bad solder joints, and probably clean up this wiring over here. That's a bit shitty too. They're sort of asking to touch each other. Alright, so here's the preamp board removed. No real cracked solder joints anyway, just a lot of crusty flux. So we'll clean all that off, give it a bit of a soak and scrub. A few little daggy bits of solder there that we'll clean up. But all in all, the board's looking pretty good condition. There's a little bit of heat damage under that dropper resistor there. That's on the other side of the board, obviously. So that's the preamp node. Comes down here. No, sorry, that's the phase inverter node. That's the preamp node there. So the phase inverter node has overheated the board a touch. So we'll just check there's no shorts in that circuit, or there may have been historical issues there and it's just the board. But that's testing okay for drift. But we might install a new one, a metal film one, and lift it up off the board a bit, just to protect that board in the future. But all in all, I think most of the work in this thing's just going to be in the cleaning before we fire it up anyway, and then we'll check for any gremlins once we've run some signal through it and go from there. So here are the connections on the preamp board. You can see they've got some bus wire, sort of like little turrets I guess, and there's generally just one wire connected to each, so there's no reason we can't just wire to the board as normal. These are in danger of shorting out to each other. There's a couple of loose strands there on that one already, you can see, and just fraying wire in general. The only one that's got 2 connections is this one here, which is the ground, but you can see through the board there that trace is a bit fatter, so I'll probably drill that hole out slightly larger, like another 1/2 mil or so, to get both those wires through that one, and then everything else can just get soldered individually from the bottom side of the board. Alright, so the bottom of the board cleaned up rather well. The top, we've replaced that bypass cap there. All the other resistors are within tolerance. We've cleaned the sockets. Those caps up on end, I'm going to leave them in, but I've cleaned up the wiring a bit. There was a lot of excess wire there before. That cap has been installed correctly instead of floating up on just tack soldered leads, and all of the wires have been terminated to the actual circuit board itself instead of those little bits of bus wire. Alright, so none of these pots had a washer under the nut. It was just the nut straight onto the panel, and as you can see it's pretty chewed up as a result. So I'm going to pop some washers on there if we've got enough room underneath. We've got a lock washer there as the star washers underneath, which take up a bit of thickness, but we should just be able to get a thin washer underneath them just to protect that surface. Alright, so remove the original Elna cap there. The existing F&T is still in circuit, but I was thinking just this isn't a great way of doing it. There's no real mechanical support. You can rip those the traces off the board pretty easily if it copped a bit of a hit. So how about we just mount the new caps on the chassis there and just run wires to where they've got to go. That way everything's mechanically supported and not relying on just the solder connections to the board. So looking at the previously replaced capacitor, you can see the terminals have just been folded on the forks and they're sort of floating in mid-air, relying on the solder to bridge the gap between the terminal and the circuit board. That one's only hanging on by the tiniest bit of pad, so not great. We'll just run wires on there so there's no mechanical requirement of strength there. Everything's supported by the actual chassis bracket. Right, so both the filter caps, dual section filter caps, have been removed now. We're going to mount them on the chassis. And I've just removed the dropper resistors. And you can see they're not in great nick. One of them's lost its coating entirely, the other one's cracked its coating. I think they're just underpowered. These look like old school 1 watt resistors, or maybe 2 watt resistors. So I'm going to put some metal films in there. Jack them up off the board a bit to allow a bit of airflow. One of them had started to desolder itself, so that's an indication that they're getting way too hot. So we'll put some slightly larger power ones, higher power rated ones up in the air to allow a bit of airflow around them. So this here is a solder connection for one of the screen grid resistors. That's one terminal, that's the other. That pad's been ripped off and there's a bit of heat damage in the area. You can see the fiberglass pattern coming out. So I reckon the screen grid's been replaced at some point. And all 4 of them are the same sort of type of resistor, so I dare say all 4 got done at the same time. Probably a result of a shorted output valve at some point in the amp's history. Okay, now it's time to vacuum the top of the board. Would have been a bit smarter to do that before I washed the bottom of the board, but never said I was smart. Now it's looking a lot better, but it's still quite a bit of residue on there from the flux on the other side, so just get in there with the long bristle brush, a bit of alcohol on there. So again, we're doing all of this without a schematic so far. Once you've looked at a few amps, well, you realise that the conditions to make a valve operate optimally or satisfactorily are pretty similar from amp to amp. Of course the construction techniques are always a bit different, but they're following the same principles, different variations upon them, but you can sort of draw a very basic schematic in your head just by looking at the thing for a little while, or in my case not so little while, because as I said, I'm not the smartest. Alright, so that's looking a lot better. All the flux residue is gone, all the dust. Still got to remove the couple of Elna caps there, the electrolytics, because they're from 1903. And then we'll look at firing this thing up, seeing how she reacts. Test for voltages first, and if we're happy that everything's present where it should be at a percentage of the input mains, we'll throw some valves in there and we'll see how she handles the load and pump some audio through it, see if there's any more gremlins to sort out. Alright champions, I went kind of crazy and traced out this entire amp as well. So here's the information off the back plate. That's just for sort of reference, it's not actual measurements. We've got the output section, output transformer as usual. Interesting setup here. We've got a driver stage which is between the phase inverter, which is just a cathodyne, and the output valves. So it's like they had some loss because it was a cathodyne, so they tried to bring it back with another another dual triode there, which was a 6 CG7, and then 12 AU 7s everywhere else. Kind of a weird setup. But a lot of these amps, like, you try and figure out what they were thinking and you just sort of go crazy. So anyway, starting down at the power supply, it's all pretty conventional down there. So we've got an active fuse there, which is good to see. We've got a dual pole single throw switch, or it was actually dual pole dual throw switch wired for the single throw. And then we've got a neon there indicating for the power lamp. This earth is the one that we moved to the chassis. Previously that went through the circuit board and all over the place and eventually connected to the chassis at the speaker end. Down here we had a center tapped 6.3 volts for the heater supply. I removed that center tap and made an artificial center tap there just to balance the heaters a bit better. Reduced the hum a little. Power supply for the bias, which isn't complete. That normally wouldn't make up a bias supply, but these other components which are attached to the valves which form the other end of the divider to ground. So I've sort of just left that out. And we've got a bridge rectified, full wave rectified HT here with a standby switch before everything. We've got a neon there, and these are the two dual section can caps, and that's the choke, which was previously shorted out, so the screen and the B plus would have been on the same node. You'd at least want a dropper there, like a dropper resistor, if you're going to bypass the choke, just so the screen doesn't try to be a plate when it gets driven hard, because that could melt it. And then you got your two 10K droppers that we replaced on the board, and your other can cap there. So this is the wire that disappears to the preamp board and supplies the whole preamp, and then this supplies only the phase inverter and its previous gain stage. So again, excuse my handwriting, this is an exercise in drawing schematics too. I want to get better at it. I'm not very good at it, and I like to practice the things I'm shit at instead of just getting a bag of Doritos and sitting on the couch. So this was sort of erased a million times to get it legible as it is, so it started off pretty bad, but it's still not great, so I've got to work on it more. I've got to think before I put the pencil on the paper. So it's just your typical output stage, 1K screen, grid resistors going to the screen supply. Your HT fuse, which it's labelled on the back, is actually just the cathode fuse for the output valves. There's no fuse in the HT supply other than that. So that's just on the cathodes of the output valves only. You got 12K grid stoppers, one per valve. Good to see. They could be lifted a bit if you wanted to reduce blocking distortion. It's like they got a deal on 47K and 100K resistors because they're everywhere. So this forms a bias balance pot, so you can really evenly balance between the two sides, because here's your bias feed coming from what I was just showing you before. That's essentially your bottom half of the resistive divider to ground, but then you got a balance here so you can swing it one way or the other. And these 47Ks at the end are essentially like end stops, so you can't go too far one way or too far away from the other. So yeah, that's pretty cool. That means you can mix and match unmatched valves and still get them pretty close. So over here we've got our driver valve, which I'm not too sure on its function other than making up for the gain lost in a cathode ion. It's also got a balance control for its plate supply, and I'm guessing that's because I guess these would act like a bit of a buffer, because with a cathode ion you're always off balance because you've got a lower impedance on the cathode than you do on the plate, so the cathode's happy to drive any impedance, whereas the plate will fall over a bit. And these sort of buffer the output valves from that, I guess, was the thinking, and you can use this balance control to vary
between the two to sort of balance up the waveform, trying to get it more even. Or in modern days where we know that perfectly even distortion sometimes doesn't sound the greatest, you could intentionally throw it off for a little bit of asymmetry to the distortion as it starts to occur. And before that, you've got another gain stage feeding into the cathodion, and it's got negative feedback coming from the 8 ohm tap feeding into here. And it's also got this, so this is my internal notes, but this just goes to a presence pot. So if you had a pot to ground there, that's all that's on the preamp board, but I just put it on the preamp schematic because it's mounted on the preamp board, just so we've got a complete set. So we've got a 1 meg grid leak here, which is pretty typical, but we've got these 100 pico caps scattered throughout. They're ceramics. It may be some attempt to stop oscillation that was occurring sometime during the design process, or maybe in production, but I would be curious to see if they went a bit further than they had to with all of these, because the thing's sounding a little bit dull. You got to crank the treble right up and the presence all the way up for it to sound decent, and in my opinion it should sound closer to that when everything's in the sort of center of its control. So here's the lineup for this, V1, 2 and 3, 12 AU 7s, and there's their roll, preamp, or gain stage. And then you got your gain stage with negative feedback and your cathodion phase inverter. 6 CG7 is output stage driver or buffer, I guess you could say, and then your 4 EL34, or in this case 6 CA7. It's the same valve, it's just a different code for it for British manufacturers, and they're just the output valves, obviously. Duh. Now here's the preamp board mounted on the front panel. You've got two pretty similar channels coming in and mixing via 100k. Like I say, they must have had a discount on 100k resistors. You got 100k plate loads, 100k mixed resistors there, and I've forgotten the value there. It wouldn't be a Brad's guitar garage schematic without a missing value somewhere, would it? But they were different values. I believe that was a 4.7 nano. But you can see the normal input's bypassed, whereas the bright input is not. However, they're still biased at the same point. You've got these 100 picos across the input even. So all of these adding up are going to pull a bit of top end out. And 100k grid leaks, which is curious. So you've got shorting jacks. That was prior to me replacing them, and I did it the same way when I replaced them. This is just showing how it came in with the ground connected to the main PCB and then going to ground via the speaker jacks, whereas now the ground's over here and this connects to the other PCB still, but there's no ground at that end, so we don't have any ground loops. So they mix into a 500k pot, and that works as the grid leak as well. And you got another 100 pico there. This is bypassed with a 1 microfarad, standard 100k plate load. All of these are off the same node, so they all 4 triodes are powered from the same node, which is the last one. Oh, sorry, second last one in the power supply. Then you've got a pretty typical, Fender Marshall Vox style tone stack, which was refreshing after the last one. And then you got a 220 pico there, which is that's like snubbing, so I guess they're trying to reduce oscillation there as well. And that's only got a 220 nano bypassed, and then a 4.7 nano to the output stage. And then up here is just indicating that the presence pot is on this board, and then has its own coax that goes to the V3A. So yeah, another kind of strange amp, but once you see a few of these architectures, you understand that it took them a while to settle on the sort of standard setups that we have in guitar amps these days. And a lot of people think, maybe we should get back and try that one out. Well, there's a reason this wasn't a classic amp. The classic amps are known for their simplicity, and just choosing exactly what they need and nothing more. With these amps, I think they were still figuring that out.